Okay, let's start. So let me remind you, in the previous lecture, we discussed local methods. We discussed a bias variance decomposition that went through a different path than uniform convergence. We did not use any maxima of empirical minus expected quantities, really. The bias variance decomposition is useful for a variety of methods, maybe not for ERM, but for other methods where you define a function in a particular way, such as k nearest neighbors. And especially it's useful when you have a closed form solution. Another method that has a closed form solution is a Nadaraya-Watson method. Do you guys mind not speaking? Thanks. So another method that I was going to talk about is a Nadaraya-Watson method. It's a local method that it is, in a sense, similar to k nearest neighbors. It's a more smooth version of k nearest neighbors. But I decided I will postpone that until another lecture. I'll make a new lecture on interpolation, if this is a subject that might be of interest to you. And I will talk about interpolation in these local methods and also interpolation using global kernel methods and minimal norm interpolation. I'll try to connect it to neural networks. Okay, so that will be a new lecture that we haven't taught last year, which means I have to sit down and find time to write it. Okay, so today I'm going to switch gears and I'm going to talk about two other methods for proving generalization bounds. So far we have a uniform convergence based methods, and that's very good for analyzing ERM. It's very easy to analyze empirical risk minimization using that method. We have the bias variance decomposition and local methods. That's useful for that set of methods. I'll present two more. Okay, so the goal is just to expose you to as many possible ways as I can of proving something useful about out-of-sample performance of your algorithm. So remember that before our goal was expected loss of f hat minus L of f star. This is the gold standard, the smallest achievable overall measurable functions, the Bayes error. That was our goal. Now, in this lecture, the goal is going to be different. So today, the goal is understand expected out-of-sample performance of f hat minus L hat of f hat. Okay? This is now our goal for this lecture. What's the meaning of this? Well, f hat is your algorithm, and what you want to know is that out-of-sample performance is close to not much worse than the in-sample performance. Okay? We do this in expectation. You can ask the same question in high probability. Okay? But the point is to try to compare out-of-sample performance to in-sample performance. Now, if I show you that this is a small quantity, is that good news or bad news for your algorithm, or can you tell? If this difference is small, then I do know that the out-of-sample is not much worse than the in-sample performance. But that doesn't really tell me anything about the actual performance of the algorithm, right? All it says is that the performance on the data is indicative of out-of-sample performance, right? But it doesn't mean that this is small, right? To contrast it with this statement, which says this is going to be small compared to the best I can do, right? Hopefully, right? So this is a much more interesting goal. This goal is more modest, and it says my out-of-sample is going to be comparable to the in-sample. Yes?
Can you
Yes, sure. This is our data set.
That's what I expect.
Yeah. Yeah, right. So just a convention, whenever one writes an expectation and doesn't specify over what variable, what you should do is you look at the random variable and see what is it measurable with respect to. Well, and this one is clearly, that goes to the first lecture, it's measurable with respect to the data set only. There is no other, right? It's just the f hat, that's the random quantity. And so this has to be over the data set. Right? Good. Other questions? Yes? That's correct. That's correct. So if you know that f hat is actually the empirical risk minimizer, and you know that the expected is close to empirical, then you're on the way to proving at least the first part of this decomposition, the estimation error, right? And so if you know that you minimize empirical risk over a class F, that's half of this, half of the job of proving this that this quantity is small, right? And for that, it's sufficient to show this. Everyone is on the same page, right? But in the literature, some people call this a generalization error. So I actually, there are different versions, so just be mindful. Some people call this the generalization error, just this quantity. This is the generalization error. It's the out-of-sample performance. And some people call this difference the generalization error. Let's call it the generalization gap. Okay, so that's a gap. So the goal today is to understand for which algorithms this gap can be small. Okay, and this might not be immediately applicable to neural networks. For instance, in this overparameterized regime that is popular now, because the in-sample is typically close to 0, but out-of-sample is not close to 0. It's like 10% on your CFAR10 or whatever ImageNet, or then you shouldn't hope to get this small, right? You shouldn't hope to have this difference small, right? So I'm only going to be talking about, let's say, other methods, and this could come useful in your research or your studies. Okay, so this is the goal.
And in practice, somebody was making this point. In practice, deep networks are also used with more data than parameters, data set.
Yes.
So with data augmentation.
Yeah. Yeah.
So that case.
Yeah. So it's not clear. I'm not convinced that overparameterized neural networks is the solution for the rest of our lives, and you know. Right. That's correct. Right. So I think it's still worth knowing how to analyze this gap, but be mindful of the fact that actually this is the object of interest, and difference being small is only interesting kind of if this is small, right? So you should be minimizing empirical fit to it. Okay, good. So what was the difficulty with analyzing this quantity? The difficulty, why is this not 0? Well, because this is a biased estimate, as we discussed. You're evaluating your performance on the very data on which you trained. So even though this is an average, in expectation, it's not equal to the out-of-sample error, right? This is real. So you can have an algorithm that just memorizes the data and outputs junk out of the data, outside of the data. So you cannot hope to have this small always, right? There are methods where this is really different. And so these two techniques that I will present today ensure that that doesn't happen. Okay, that the way that they work is that they limit the dependence on of f hat on the data. Somehow the memorization example where you just memorize the data and then output junk outside of the data, that's an extreme dependence on the data set, right? And so now the question, can we limit this dependence on the data set? And if we do limit the dependence on the data set, then maybe the central limit theorem starts to kick in, right? The central limit theorem would say that this is close to that, you know, of the order of 1 over square root of n, and in terms of expectation, this becomes more or less biased version of this, right? So both of these approaches will make this a less biased version of the out-of-sample performance. Okay. I'm going to again switch to our G notation instead of L of F. So whenever we had loss of F like this, I'm going to replace it by G. So the XY pair is going to be replaced by Z. The class L composed, loss composed with F is going to be the class G. Although we're not really going to be working with any class for the purposes of this, so maybe this is not relevant. I'm going to write L composed with F hat. I'm just going to denote this as a G hat. Okay, that's going to be the notation. So then my goal, I can rewrite this as a expectation over the data set. Now, of course, the data set S is just Z1 through Zn. Right. So at this point, we don't care about the fact that these are XY pairs, and the analysis will be general enough. Expected over S of expected G of Z, but this is a G hat, minus 1 over N sum of G hat Z I, right? Where G hat is a G hat of the data set, right? So let me again unpack this notation. All I did is just replaced these definitions as a shorthand. That's just expectation over Z. G hat of Z minus 1/2 average of G hat Zi. And it's important to remember that G hat is a function of all the data. Okay? Is everyone comfortable with this notation, with the shorthand? Okay. I'm going to put a subscript N on all the algorithms and on the G as well, because we will have varying size of data set N. Okay. Questions about this notation? Yes. Yes. Yeah, that's a good point. So if my goal is to estimate this, then I just take I leave out some data and then I use that. So the goal is not really to evaluate, but understand conditions under which conditions on the algorithm under which I wouldn't have to do that in some sense, right? Because often in practice, people track the in-sample performance. They optimize for the in-sample performance. It would be nice to know that's also optimizing somehow for out-of-sample performance. But again, this is a great point that what you should be doing, of course, is to have a data set that you only use once. Right? And there's a whole discussion, we can do the whole lecture on using the holdout data set more than once and the problems that arise and so forth. Okay, good. So, so let's see, what is a compression bound? So the compression approach is very simple. So suppose there is a function, a compression function, or a selection function C, which takes as the input the data set S and outputs a subset of that data set. So let's write it as a subset of S, okay? And let's subscript this with a k. K is a parameter that will be fixed throughout the lecture. And the size of this ck of S is always at most k for any data set S. Okay? Yeah, so just a function that selects from this subset. So assumption on the algorithm. Assumption on the algorithm. I want to codify the assumption that the algorithm really only depends on this subset. Okay? My algorithm, there exists a subset of the data, so that the algorithm only depends on this subset. Okay? Well, so I'm saying that consider an algorithm with this assumption. I'm going to assume that the algorithm. So I know that I cannot upper bound this in general because of examples that I've given you, like memorization. So the question is, what assumption on the algorithm would rule out and allow me to get an upper bound? The algorithm depends. Yeah.
It's a predetermined set that we don't know.
So let me write it down, and then we'll discuss. So g of n, g hat, right? That's our algorithm. Actually, it's the loss of the algorithm, but it doesn't matter. Now, this depends on the data, right? So this is a function of S. And what I'm going to say is that it's the same function that you would have gotten if you ran this algorithm just with k data points based on ck of S. Okay? Yes?
But you can always like commute the data points, right?
So this is a selection function.
So it looks at the data.
Yes, yeah, right. So I'm just going to think of this as a map from the data set. Now you're asking whether it's an ordered data set or not. Let's say it's an unordered data set. So that might put some restrictions on the algorithm. Let me give you an example. So
what if k is not? What if the subset doesn't have exactly k points? Then what do we say?
yeah, I guess less than or equal to less than, yeah, okay. Right. Should we just say equal? Let's say equal. Let me not worry about this. Okay, we can redefine it with a less than or equal here. Less than or equal. Okay. So let me give an example. So suppose that you have pluses. And these are the cats, and in fact, dogs are all somehow in some subset in a rectangle. So this is, if you know the PAC framework, your examples are labeled according to some rectangle. So what's inside is minus, outside is a plus. Okay. Now, of course, I don't know this rectangle. All I see is the data. And I'm going to minimize my empirical loss over this data set, and I get to work with rectangles. So my model is well specified in that language. or not agnostic. So, well, I'm going to have an algorithm that constructs a rectangle. That's my hypothesis. Picks the rectangle that minimizes the data. And the claim is that if I threw out all the data except for the leftmost, for the four leftmost, rightmost, topmost, etc. points, I would get the same rectangle, given that I define my algorithm correctly, that it's minimizing the error and kind of it's the smallest one, right? Otherwise, I have to provide you a choice of the empirical minimizer. There are many here. So that's an example, right? Here there is a compression of the data set of size 4. Of course, there is a strong assumption that the data are separable, okay, in this particular example. But there is a compression of size 4. I can throw out all the data, and my algorithm would only depend on that subset. Right? Any questions about this? What's another example? Well, another example is perceptron. Remember, when we run it repeatedly on a sequence, it makes a finite number of mistakes. And whether the other points on which it correctly classified, whether they were there or not, doesn't matter. Another example is support vector machine. The hyperplane, if you know that, the hyperplane is defined according to support vectors. And anything other than support vectors, if you throw it out, it would be the same solution. Right? So there are a number of examples where such a compression is plausible. Whether this is true in neural networks, I don't know. That's for you to investigate.
But you have to know what they are, or just that they exist?
I just need that they exist. Yeah, I don't need to know what they are. Yes? Yeah, I think it's both. It's on the data, let's say separable. Like the perceptron wouldn't work if it's not separable. So it's both on the data and potentially the data generating mechanism and on the algorithm. That's correct. Yes.
There's an example that's only on the algorithm, like the linear programming. If you have n constraints in d dimensions, then only d constraints can ever define the algorithm.
Right. And I think I'll give one more example that will only depend on the algorithm. Okay. Good. Okay. So my claim is that in such a case, if k is small, then this is mostly out of sample, right? This quantity is mostly out of sample. So let's try to quantify. So this is a less biased version of this than if you have a full dependence. Let's just try to kind of quantify this. Make sense? Yeah. All right. So my goal is remember. So my goal is to understand the expectation over the data set S. Okay, there are several ways of doing this. Let me do one way. And maybe I'll even leave part of this for you to fill in at home as a homework. Gn hat of z minus 1 over n g hat n of zi, right? That's our goal. So let's continue. So expectation over S. Again, I think it might be more interesting actually to consider hyperability instead of inexpectation over S. So you can modify whatever I'm going to say to hold with hyperability instead of inexpectation. Now, by assumption, this is equal to g hat k of. Okay. Now I have double parentheses, right? I need to specify what this depends on. This depended on set S. Now this one depends on the subset C k of S. But it's a function, so I evaluate it at Z. Okay. minus 1 over n sum g hat n g hat k, sorry, of c k of s evaluated at zi. Okay. And now what I'm going to do is, okay, this is one way of doing this. I'm just going to upper bound this by expected over s max subset I subset of 1 through n of size less than k, or equal to k if you don't want to, if you want to be more precise. Okay, so again, I just want to remove this dependence. I don't want to worry about the about this dependence. So S sub I is just a subset of the set Zi I in I. And we get Z minus 1 over n sum G hat K S I of Zi. So now it's a little bit easier to think about this quantity, because I can say, okay, let me fix I. I fix a subset, okay? And now I see that this is mostly out of sample if the size of I is small, right? This is mostly, the expectation of this is mostly that, right? Most of these quantities, most of the ZIs do not appear in SI if SI is small. So this is an out of sample, right? That's the average of almost independent variables. Yes?
Like ZIs are like literally from SI, right? Or
Yeah, ZIs are from S.
you just said that like ZIs are both from SI.
No, right. So there will be some of them from SI, but the size of SI is small. So imagine that that K is 1, right? So what? Okay, K is 2. Let's say K is 2. So I'm picking the worst 2 elements from the data set, and I'm asking if my function depends on those 2 elements. Let me evaluate it on the other elements, but this function hasn't seen the n minus 2 elements. So this is mostly out of sample, right? Make sense? So now this is a almost zero mean random variable. Maximum of n, oh, n is a bad number. A max of f random variables, a zero mean sub-Gaussian random variable scales like square root of log f. Okay, that's something maybe I think I already asked it on the homework 3, right? So the maximum scales as square root of log cardinality, right? Okay, except I have to deal with those elements that where Zi does enter in Si, right? But there are only k of them. So I'm gonna assume that functions, the loss functions, are bounded. So suppose the G's is in A, B. The range of these functions, the range of G hat for any sus, let's say K, the range of G hat is between A and B. Just bounded functions, right? So the loss is bounded. Now, of course, for square, that's not going to happen unless the F's are bounded and the Y's are bounded. It's kind of a cheap assumption that I'm going to make. So there are k elements that are indeed in Si, and I don't know what to do with them. So what I'm going to do is I'm going to replace them with fresh samples. In that case, this is really an unbiased estimate of that. In expectation, this is equal to that, and that's the average of independent. And now I'm left over with average of k in sample versus out of sample, and that's bounded by k times b minus a over n. So what I get is I lose k times b minus a over n. And let me make this, I'm skipping constants, plus square root of log. So how many subsets are there? N choose k over n, because that's the central limit theorem, 1 over square root of n. Just took a union bound, pretty much what you did in, or what you're doing in homework 3. Right? I skipped a few details. Maybe I'll leave that for the homework. I hope the idea is clear. Right? It's mostly out of sample. If you replace these k guys that k of these zi's that are problematic because they enter in this set, you lose that much under this boundedness assumption, but then you the rest is a maximum of n choose k zero mean random variables with variance 1 over n. Okay, question.
I think there might be something weird going on with the condition.
Okay.
If you look at the random choice I, it's the worst case. The rest of the variables don't tell you, and this is really true that it shouldn't tell you about the generalization because the I is chosen so that these variables will tell you as the robot generalization. It is the worst case.
I'm trying to interpret your question. So maybe a way to think about this is as follows. Let me think of this as a random variable indexed by I. And you can just think about a single fixed random variable for the given I. So suppose that the I is the first k elements. So now I'm asking if my algorithm just looks at these first k elements, and that is the function computed by that algorithm. Okay? So the choice of I is really fixed. That's the way to think about this. That's actually the reason we went to max, because otherwise it's complicated. Once you go to the max, it's the worst case, and think of this as fixed now. So this function looks at the first k, but it's being evaluated on all of them, and it can only be bad on the first k. Does that make sense?
So how did you get the b minus a?
Oh, this is just the absolute kind of the scale. The how bad can this be versus a new random draw of the data set that I replace whatever is in SI, I replace it with some fresh data. Yes.
Let's say we substitute our algorithm to use the worst KI subset.
Okay.
So that algorithm also enjoys this analysis, right?
Right. Right.
But the generalization error of that algorithm is something very bad. The true generalization, not this one.
Why is that the case? So
Like you use the worst K.
yes.
You use the worst I. So, for example, in that
Mhm.
example, you use the center minus.
But I need to make sure that it gives me a function that would be the same function if I just gave it that subset, right? Then it doesn't depend on the rest of the data points.
Yes. So we only use the K worst.
Yeah. So why is generalization bad for that algorithm? Why do you feel that, right, the generalization should be bad for that?
Because those k elements might not be within k. I mean, in that rectangle.
But I'm looking for the okay.
In that rectangle example, like there is certainly a substance k that's.
Yes, but the empirical is close to expected. I'm not saying that the expected will be good. I'm just saying that the empirical is going to be close to expected. Right? It might be a bad algorithm.
Yeah, that's what I mean. Like this quantity still is small for that algorithm, according to this analysis.
Yes.
But the true generalization error of that algorithm is very bad.
Why is that?
Just the intuition that like if you take the worst case I, why should it be a good? I mean, among all the sets I, assume the one that has the least information.
Okay. We can take it offline. Yeah. Yes.
If you replace like the condition on G, instead of being between A and B, like set some variance condition,
Yeah.
will you get the same bound?
Yeah. No, so it's not clear actually. This path is unclear. Maybe there is some other path. The way I was thinking is just substituting the ZIs with fresh samples, but then you need pointwise control. There might. I just don't want to think of this as a random subset anymore. So I want to think of this as just as a, first k elements. If I can do it for the first k elements, then I pay a log factor, and I can do it for all k subsets. Yes. Yeah. That's all I'm doing. Yes.
Well, look at this where the logarithm comes from.
Oh, so if you've got a u1, let's say d, zero mean, and sub-Gaussian. So what is sub-Gaussian? Okay, I don't want to write the technical definition. It has decaying tails. Then the expected max of ui behaves up to constant like the sigma, which is the parameter of sub-Gaussianity, which is 1 over square root of n in this case, because that's what you get from averaging, times square root of log d. Okay, that's the result. Yes. Other questions? Think of d-Gaussians. The expected maximum of d of them grows with d if they're independent. But it grows algorithmically only, square root of log.
Are you using something from like extremal distribution of Gaussians here, or?
It's a simple result. I think it's actually in homework 3, or a version of this is in the homework 3. At least the probability version is in homework 3, and then you can integrate the tail to get the expectation. Okay, all right, so let me move on. Right, so here's another example of a example thresholds in 1D. This is a class we've looked at before, but so now my data is a bunch of real valued x's colored with plus, plus, minus, 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 plus, plus, minus, minus, and so forth. Okay, so that's my training data, just like that rectangle. And I'm doing empirical risk minimization. So I'm going to try to find a threshold that minimizes the number of mistakes in the data. And let's say I pick the midpoint of the 2 data points just to make it well defined. So let's say like that. This is going to be my minimizer, and it has the property that the plus has to be on the left of the minus. Otherwise, I can improve the by 2 over n, my empirical fit to data, or 1 over n. Now, what if I threw away all the data points except for these 2? I would get the same classifier. So there is a compression of size 2. So the generalization gap is log n choose 2. Anyway, log n choose k is like k log n, right? So we get k log n. Here it's log n over, on the order of log n over n. And that's the same result that we've got with VC-based bounds. In fact, if you think of this as a k log n, then really k kind of plays the role of VC. But the connection is not as between VC and the existence of a compression set has been an open problem for a long time, and I suggest that you do not work on it. It's a big waste of time.
Can you just quickly explain your choice of the minimizer here? Like, what did you do?
I was sliding the threshold
Yeah.
until it was the minimum empirical loss. So I'm classifying everything to the left as, let's say, minus, everything to the right as a plus. So that has 1, 2, I don't know, maybe 2 or 3 mistakes, 4 mistakes. That's the minimum.
Claim that it has to be plus on this side and minus on the other side.
If it's minus on the left and plus on the right, well, okay, it depends on which way we're going. You can improve it, right?
Okay. But so then this means it's always 2.
The compression size is 2, yeah.
There were cases that is found better than VC dimension.
I don't know any cases where this bound is better. Well, okay, so this bound actually is closely related to the margin bound. Okay, because 1 over gamma squared is the number of mistakes. If you think about this analysis, it's very much similar to the analysis we had before, where you cycle through the data, and there are only that 1 over gamma squared number of mistakes. That's the number of corrections, so you can compress to that data set and get the same hypothesis, right? So if you think about the perceptron, 1 over gamma squared is k for that case. So now you're asking, for instance, in that case, is 1 over gamma squared better than the VC analysis? Yes, it is better. Well, it can be better because it doesn't depend on the ambient dimension. It depends on the margin. So it depends on some properties of the data rather than on the ambient dimension. Can it be worse than, yeah, I mean, for instance, the margin can be worse than in small dimension. Except we're vaguely talking about VC because there are other VC variants, like scale sensitive dimension, that can recover the gamma margin result. So I don't want to label as this being worse or better than VC. Okay, other questions? Okay, now a little bit more maybe interesting, I don't know, is the second one, which is the stability, algorithmic stability. So again, just to recap, what we're doing now is we're really doing algorithmic centered analysis. You give me an algorithm, I'm going to try to see if it has a compression bound or an algorithmic stability. And if it does, then maybe there is a hope to show that empirical is not too far from expected. Algorithmic stability is another version of a algorithm doesn't depend too much on the data, but instead of depending only on a subset of k data points, what we're going to say is that the algorithm doesn't depend on any particular one too much, okay, on any particular data point too much. To start the analysis, let me just start with this, with our goal. So now stability. G n hat. Okay, I want to expect it. Okay, so what I want to do now is I want to separately develop these two terms. So the first term is expected over S, expected over Z, and this is over Z, Gn hat of Z1, I'm going to write out the Zn, of Z. Yeah? Now, I'm going to assume that the algorithm is symmetric. Symmetric means that the algorithm doesn't look at the order of the data. What matters is the collection of the data, not the order. This is extra parentheses. I don't need. Now, so S is Z1 through Zn, and now I got one more. Think of this as the n plus 1th point. All of these are just names, right, for variables. These are just dummy variables, right? So I can, in particular, I can rename Z and Z1. These are just names, right? I can put whatever I want. So I'm just going to rename it for purposes that will be clearer later. So this is expectation over Z1, Zn, and Z, G hat n of Z, Z2, Zn of Z1. So I haven't changed anything. All I did is just to rename. Okay. And the meaning is still the same. This is out of sample, in expectation, out of sample performance, because the algorithm doesn't know about Z1. Now the other one is more interesting. Expectation over data set of 1 over n, sum of G n hat of Z1 through Zn, evaluated on Zi. Okay. Now this is equal to 1 over n sum I from 1 to n expectation G hat n of Z1 up to Zn evaluated on Zi. I haven't done anything except push the expectation in. Okay, so I take an expectation over the data set. I look at the function trained on the data and evaluate it on the ith point. But because this algorithm is symmetric, all of these terms are the same. Okay, the order doesn't matter. Just by symmetry, it's clear that this is equal to expected over the data set G hat n trained on Z1, Zn, and evaluated on, let's say, Z1. I can pick any one, but let's pick Z1. Okay, so our goal, or expected generalization gap, as we agreed to call it for our algorithm, is at most, now I'm gonna bring these two together again, expected over the set S and Z, G hat and Z1, Z, comma Z2, Zn, evaluated at Z1, minus G hat N, trained on Z1, Z2, Zn, and evaluated at Z1. Okay. It's a bit of magic. It's not really magic, it's just renaming, a bunch of renaming. Okay. Any questions about this? Yes. Oh, it's equality, yes, thank you. That's important. It's equality. Thank you. It's equality. Now, this is just rewriting, right? This is equality. And all that this is saying is that if I want to get an expectation, empirical performance and expected performance of my algorithm close, well, it better be the case that on average, when I look at the algorithm and I replace the first data point by something else, the evaluation on a point that's inside versus outside of the data set, it doesn't change too much, right? So that's a notion of stability. This is a notion of stability. Stability of an algorithm. If the algorithm, when you flip the first coordinate or the first element of the data set, if you change it, then evaluation on that data doesn't change too much, then you've got empirical close to expected.
So you remove one point,
Yeah,
and replace it with something else, and then you evaluate on that point.
yes, yes.
And it doesn't change it.
That's right, that's right. And it kind of makes sense, right?
It doesn't change much? Or?
Yeah, so this is all equality.
Yeah.
So it has to be the case. It's if and only if. Even only if this is small, you will get that difference in expectation small. So,
Is that what you assume when you say that?
yeah, so I'm gonna show that reproducing kernel methods, the regularization methods, have a much stronger stability than this, and that will imply this expected generalization gap being small. Okay, I mean, if you think about this, yeah.
Important to say that we like this gap to go smaller and smaller as I
That's right. So I want something that upper bounds this quantity, something that goes down with n, ideally. Yes, that's correct. Okay, so this is the notion of stability that is equivalent to generalization. And it kind of makes sense, and we haven't really done much. We just rename things. And what this says is the value of the function, whether the element is in the data set or not in the data set, should be similar, which is very similar to what we were asking, right? Whether you're in a data set or not, my function will not change its prediction too much on you, right? That's the meaning of the stability. Yes.
Since we're taking it into expectation over the whole Z in this case, isn't that a sort of comment about the data as well? Because
The data and the new point. So on average, over the draw of the data and the new data point, whether the data point Z1 was or was not in the training data set, on average, the values on that data point should be similar.
If you bound what's inside the brackets, you don't really care about SMC anymore, right? If
Yeah,
you say
yeah. So what
that-
right? So what we're gonna do is a much stronger condition. Uniform beta stability. So an algorithm is uniformly beta stable if for any data set S, any I, and any, let's say, substitute that I will put in, Z, let's call it ZI. Oh, I know, Z prime I, let's call it Z prime I. The function G hat N Z1 Z, right, I'm gonna do the same thing. Z I prime Zn evaluated at Z minus G hat N Z1 Zi Zn at Z less than beta. Let me just check that didn't make a mistake. These are just names. I guess I swapped the names of Zi and Z again. Yeah, I think this is correct.
Basically, you're saying replace ZI by a fresh point.
Yep.
and
In the
evaluate
training.
on any Z,
And any Z, yeah,
not ZI.
that's correct. Right. That's a stronger notion. Yeah.
So basically, you're saying if you drop one data, like if you place one data point,
By something else.
it doesn't change it.
Exactly.
That's the assumption.
That's the assumption. It's a much stronger assumption than what's needed. And if you know about differential privacy, which we'll cover in the next lecture, this is starting to look like differential privacy. The output of my algorithm doesn't depend too much on any particular data point. So if you're not in my database, I'll give out a randomized answer, which you can't really distinguish too much from if you were in the database. Except these are deterministic algorithms, and so for randomized, we'll talk next time about this. Oh, maybe I should erase this instead. It doesn't matter. Okay.
Do we hope for beta to become smaller with n?
That's correct. That's correct. So I'm not going to write it, but clearly this condition implies that that's upper bounded by beta. Right? That should be clear. Okay, so kernel ridge regression is beta uniformly stable with beta equals to, okay, it's order of 1 over lambda n. So let me remind you what lambda is. F hat n is argmin over f in h, 1 over n, sum of f of xi minus yi squared plus lambda, the norm of the function in the RKHS. Okay, so Lorenzo covered this this method from the algorithmic point of view, and now we want to understand if we can take a shortcut and prove the generalization gap.
This is lambda to the power n or times
No, times n, sorry, times n. Yeah. So it's 1 over lambda n. Okay, and we will assume that the ridge of the kernel is bounded by some kappa squared. Okay, so that's a limit on how big our functions can get, the ridge of the kernel. Okay, so what's the idea? Let me first describe the kind of a high-level idea of this. We need to understand what happens if I replace one data point xi, yi in this objective. How does the solution change? So I'm going to denote the data set S as the xi, yi pairs, and S prime will be the one where y1, but then the xi pair is replaced by the zi prime, xn, yn. Okay, and now f hat n will be the solution with these data, and f hat prime n will be the solution with this data set. Right, so with this notation, what we want to understand is whether the loss function, but okay, the loss difference being bounded by beta will be implied by some closeness of f hat n and f hat prime n pointwise for all the z's. Okay, so we'll get an L infinity. This is like an L infinity bound between these functions, right? Because it's for every z. Did I write for every z? Sorry. Let me write for every z. So this is true for every z. So we will show that that f hat n minus f hat n prime in the L infinity sense is bounded by order of 1 over lambda n. Okay? So this is an interesting connection to ill-posed problems for ill-posed inverse problems, because you're working with infinite dimensional space. There are too many solutions that go through the data points. You're adding a regularizer, and now hope that the regularizer goes to 0 with n. That's what we will typically do, or cross-validate this lambda. But this regularizer also ensures stability, and that's what we're going to prove. The stability in this sense, in a very strong sense. By the way, the analysis that I'm going to write down is due to Bousquet and Eliseev in 2002. The paper is called Stability and Generalization. After that, there was a series of works by Tommy and others around 2005. Then there was a gap of maybe 6 years. There was another result on stability. And then differential privacy really came back with its notions of randomized stability, or a stability of randomized algorithms. And so there was some kind of resurgence in the last 5 years of stability-based analysis. Okay, so that's a bit of history, but this actually first definitions of stability for the analysis of local methods go back to what is it, 70s, 80s maybe, by Devroy and Wagner. I can give all those references. Okay, so let's try to prove this in the remaining 15 minutes.
Can you explain this? So the max here is you take it over what?
Over all the x's. So point-wise over all the x's.
The x is an s or an s prime?
All the x's. Yeah. We need some assumptions. As we go, we'll point out the assumptions that we need to make this work. So what this is saying is really that these two functions are point-wise close in L-infinity sense. And that will imply, if the y variable is also bounded, that will also imply that the losses are bounded, which is what we need here.
And also, don't we need to specify what the kernel is? Or
So it works for any kernel as long as the ridge is bounded. Okay, there might be some technical assumptions that we'll find as we go. Okay, so here's the proof, and the idea is that this objective, which I'm going to denote as a phi of f. This objective is strongly convex in f. Okay, so I need to tell you what strong convexity is. And when I replace the data set, when I replace one data point in this average, I'm going to denote this as a phi prime of f. Okay, that objective. So we'll have two objectives. And let me do proof by picture first. Proof by picture is that this phi of f is strongly convex. So think of this as a rising fast. More precisely, I'll write down it lies above the first order approximation plus some second order term as well. So it's at least as fast as a quadratic. And then we have a perturbed objective, phi prime, right? That's the one where we replaced one data point. Yeah. So that's going to be like that. And we have two minimizers. This is f hat n, and this is f hat prime n. This is the phi prime of f. These are the two minimizers. So if I could ensure that these gaps are small, you can see that this pins down the distance between these functions, between these points, because the function goes up too quickly. If it was flat, then it's possible that I have this bound here, but because it's flat, the two minimizers are far away. But because the function goes up very quickly, this distance being small implies that this distance is also small. Okay, you can almost feel it, right? Okay, so let's make this precise. It's really a 5-line argument. So what is strong convexity? So we'll say that a function phi is sigma strongly convex, okay, it should be specified on some domain, let's say W, if for any u and v in this W, phi of u lies above what you would guess if this was a quadratic, right? So the phi of v plus the first order Taylor u minus v plus sigma over 2 u minus v squared. Okay, so this is with respect to this particular norm, which in our case is the RKHS norm. Okay, the definition is clear. So in this case, phi of f hat prime n is more than, just by using the definition, phi of f hat n plus, what is this term? I know that phi hat n is the minimizer, and my function is smooth, so it's 0. So the term is 0. So I can forget about this one and just write sigma over 2 f hat n prime minus f hat n squared. This is the RKHS norm. But on the other hand, phi prime of f hat n similarly is upper bounded by phi prime of f hat n prime, but this is the minimizer of this function. So again, the cross term is 0. The first order term is 0. Sigma over 2 f hat prime n minus f hat n. Okay. So if I add them up, I get that sigma times f hat prime n minus f hat n squared k is upper bounded by, okay, so it's phi of f hat prime n minus phi prime of f hat prime n plus phi prime of f hat n minus phi of f hat n. I just regrouped the two terms according to the argument rather than the function itself. But this is exactly this vertical distance or this vertical distance. And the second term is this vertical distance, right? So we just put in words, we put in mathematics what we said in words and drew in the picture, yeah? Yeah. Phi prime of f, yes, it's the one where you replace the ith guy by this new one, yeah. Yeah, okay, so I'm shoving a little bit under a bit of things under the rug, but everything works because this is the Hilbert space. Everything is nice. Essentially, it's an infinite dimensional Euclidean type. Okay. Yes. That's correct. Right. That's correct. So strong convexity. Okay, it's just a fact that the strong convexity is, if you add a quadratic, that gives at least that much strong convexity. It's clear from the definition. So the strong convexity, well, I'm dividing by 2 there, sigma. So both of these objectives are at least 2 lambda strongly convex. So both 2 lambda strongly convex. 2 coming because typically you divide by 2 here. So that's where 2 comes from. Okay, but what is the difference between these 2 objectives, right? When I look at a function and I look at the difference of phi and phi prime at this function, the norms cancel because it's the same function. All the terms that are common in the data cancel, and I'm only left with a difference of 2 losses, right? All right. In this objective, the phi prime only has 1 term that's different, that corresponds to xi prime, yi prime. So what I get is that the 2 lambda times f hat n minus f hat n prime squared k is upper bounded by, okay, so f hat n prime of xi minus yi squared minus f hat n xi minus yi squared plus f hat n xi prime minus yi squared minus f hat n of xi prime minus yi prime squared. This is prime. Okay? Now this is at most a constant times an L infinity norm right? So what I'm going to do is I'm going to write a squared minus b squared as a minus b times a plus b. And I'm going to make an assumption that a plus b is bounded, so that this plus that is bounded. So for that I need that the ridge is bounded. Right? The functions themselves are bounded. And the y variable is bounded. Okay? So let me skip those details. You can fill them in later. But you get this bound. Okay? Yes. Oh yes, this one. Yeah. This one is. Actually, I want to regroup now based on the data point. So what I want to do is, I think this one is missing the prime. Yes, this one is missing the prime. Thanks. Okay. Fact that the L infinity norm of a function is bounded by kappa times the RKHS norm of the function. It's easy to prove that this is a kappa. And this is the RKHS norm. Kappa is the ridge of the squared. Kappa squared is the bound on the ridge of the kernel. Okay, that's easy to prove. I put it in the notes. But essentially, that's all we need. Why? Because what we have now is that, there's 1 over n missing, right? I forgot 1 over n. All of these are 1 over n, scaled by 1 over n, right? So I'm going to make it correct by multiplying this by n. And now I put everything together. Actually, it's enough information. You can put these together. This is literally just plugging in everything. Okay. So the bottom line is that kernel ridge regression, because of this regularizer, is a stable procedure in a very strong sense. That when you change one data point, the functions don't change too much. And if that's the case, you would expect empirical close to expected. Now, is this the goal, to have empirical close to expected? No, I can take a constant function that doesn't look at the data, empirical close to expected, right? So it's important to keep in mind that This is only interesting if if the algorithm is doing something clever. Well, our kernel ridge regression is a clever algorithm, so it's nice to know that for that algorithm, empirical is close to expected. Yes. Yep. Go ahead.
Is there a way to go backwards? Like, if you assume this beta stability, can you also assume it's like convex or it has some nice properties?
Well, that beta stability doesn't have any structure, right? So you need to assume some structure. This is a very structured RKHS, based on norms in the RKHS space. In general, I think it's not possible to do that. But I should mention that there has been some exciting work by within the community, especially by Vitaly Feldman and Jan Wondrak at respectively Google and Stanford. They've proved high probability versions as high probability bounds on the gap based on beta stability, and it's a very nice set of results. And there's yet another paper just a few weeks ago that appeared on arXiv closing even more the gap. So, this is still an active area of research, even almost 20 years after the initial work of Bousquet and LSAF. Okay. Yes. Yes, that's right. So typically lambda is a function of n, a decreasing function of n, because with more data you want to regularize less and less. So that should be taken into account because the beta is 1 over, it's not really 1 over n, it's really 1 over something less than n, right?
Lambda should, I guess, grow less than,
Yeah, that's right. So 1 over square root of n or something like that. Yes. It's a one-line computation. It's in the slides.
So here, I mean, like you showed a lower bound on the infinity norm. We need an upper bound.
Well, this is upper bounded by RKHS norm of that, but this is square. Square cancels, and you got the result. One power cancels. Okay.